Today's warm-up question says, a neutral rod is brought near a neutral electroscope in diagram S, and causes its leaves to move as shown by T. So you've got two diagrams there, S and T. You see the same thing in the warm-up assignment, and it says describe the charge of the leaves in T. This is actually one of the simulations that you were supposed to look at yesterday in the assignment 1103. So hopefully this looks familiar. The electroscope looks slightly different in the simulation than it does in this picture, but it's the same idea. Basically, you have a metal ball or disc on top, a metal rod, and then these like foil leaves, these really lightweight material at the bottom. And what an electroscope does is it is going to show whether an object has a charge, carries a charge. So if you bring a charged object near it, in this case a positive rod, what happens is if there's a positive rod here, again we've talked about this, opposites attract and like charges repel. It's only the electrons that are capable of moving, and so when you bring this positive rod nearby, opposites attract, electrons rush up into the top of the electroscope, meaning that the leaves at the bottom don't have as many electrons as protons anymore because they've sent them up to the top. And so the leaves at the bottom end up being positively charged because they lost electrons as the electrons traveled closer to the positive rod. And so that's exactly what happens. The leaves are both positively charged, and because they're both positive now, like charges repel, and you get them flaring outward. And so it works the same way whether you bring a negative object nearby or a positive object nearby. It looks exactly the same. It's just the direction that the electrons move. And so again, that's something that you should have seen in the assignment yesterday. If you didn't finish that one, please look at it. You really do need to, it's a lot easier to understand when you can see the charges moving, which is why the simulations can be so helpful, or probably videos if you couldn't get them to load. But anyway, so that is your answer to the warm-up. The charge in the leaves in case T would be both positively charged, both of them. That is why they are repelling one another. All right, guys, today we're going to talk about charging by friction and charging by conduction. And then tomorrow we'll talk a little bit more about charging with charging by induction. You do have a assignment today, 1102.2 charging problem set, which you'll have some time to work on at the end of the period. So again, this is from the simulation the other day. Here's that negative, which it asked about a positive rod, sorry. But here's showing what happens when a negative rod is brought nearby. Here's the positive rod. And it's exactly what we just described. When you bring a positive rod nearby, this is the warm-up question basically at the bottom. Electrons move up into the metal ball or disc at the top, leaving a lack of electrons in the leaves, which is why they move apart that way. And so that same motion, you're going to see it looks exactly the same. Obviously, in real life, you can't see electrons. So whether the object is positive or negative, the electroscope behaves the same way from your perspective. But it's actually different charges depending on what you bring nearby. Here's an actual electroscope. I don't know if you can see it very well. If you have it on your own screen, I know you can. But these are little pieces of foil, and as this comb is brought nearby, the comb has a charge, and it would, if you comb your hair with it, you can build up a charge, which is what we're talking about today, charging by friction. And when that happens, the comb has a charge, and it causes one of these two things to happen. Again, I don't know what the charge of the comb is, but I do know it has one. Okay, it's either negative or positive because it's causing the electroscope to react. And again, it reacts, the leaves flare out whether you bring a negative object nearby or a positive object nearby. All right, so again, electrons are capable of transferring from one object to another, which is how the comb ended up with the charge in that last one, or like this little girl, this cute little girl on the slide, crazy hair at the end, because it's the same idea. There is a transfer of charge, and her body is getting either losing a bunch of electrons or gaining them. We're going to look at which way those things move in a second. But this is causing her hair to become charged, and it's standing on end, kind of like it was when we touched the Van de Graaff generator before spring break, and you got filled with a charge if you tried that out. And you could feel the same thing, maybe on your arms, because it feels kind of tingly as the arm hair stands up, or if you had fine straight hair, you could see it on your head like this little girl. But you can have electrons transferring by friction, by conduction, and by induction. And we're going to focus on the first two today, and we'll save induction for later. So let's start with transfer of charge by friction. Again, electrons are capable of transferring from one object to another. And one of the ways that happens is literally by rubbing two things together. It's actually how the Van de Graaff generator works as well. That belt inside that was rotating was rubbing against these combs that were inside of it. You couldn't see it happening, but it's what was happening. Or the little girl on the slide, her clothing rubbing against the plastic material that the slide was made out of, or a comb in your hair, or whatever. In this one, it has a rag and some PVC pipe. And when you rub two objects together, one of them could strip electrons from the other. Again, it depends on how strongly it attracts electrons. Different materials attract electrons more strongly than others. And so if you rub two of those materials together and one of them has a stronger affinity for electrons, it will strip them away. And that's what you see here. As this PVC is rubbed against this rag, it strips electrons off of the rag, leaving the PVC with a bunch of extra electrons and a negative charge, whereas the rag ends up having lost a bunch of electrons, now has a positive charge. You see charging by friction typically with insulators, but it doesn't have to be. But you can rub two things that aren't metal together and charge them up. Now, could you do it with metal? Sure, it just discharges a lot easier. It doesn't build the charge as well, which is why it says it's typically done with two insulators. Here is a video showing Bill Nye doing the same thing, but I just realized my sound is not in the right spot. So give me a second because I need to hook it up to the right spot.
Rub a balloon on your hair and bring it near another balloon hanging by a string. There's an invisible field pushing the two balloons apart. When you rub the balloon on your hair, you're transferring electrons from your hair onto the surface of the balloon. Now, the balloon's made of rubber. Electrons don't flow through it the way they do through a metal wire. Instead, they stay on the surface of the rubber. We use the word static electricity, which means electricity that stays. Now, different materials have different properties. Here's a stiff rubber rod and a piece of fur. It's like rubbing a rubber balloon on my hair. It also will push the balloon away. But watch what happens when I use the same piece of fur and this glass rod. It pulls the balloon toward it. So in the first case, we say they have like charges, like static charges, so they repel. In this case, they have opposite static charges, so they attract.
Okay, so again, that's the same idea. You can charge up these objects by friction. Some of them tend to become positive, some of them tend to become negative. And again, you're still going to see that same opposites attract, like charges repel thing. Now, the way you know whether the objects gain a positive or negative charge, you're not going to have to memorize it, but you can use a list like this. This is called a triboelectric series, and it ranks different materials on the basis of whether they typically become positive or typically become negative. And so you have to be able to read and interpret it. You don't have to memorize it. Some substances tend to gain electrons, whereas others lose them. So the ones up here at the top, like your skin, your hand, glass, your hair, these things typically become positively charged, which means they're typically losing electrons. Your hair readily gives up electrons. Whereas objects toward the bottom, this very last one, by the way, polyvinyl chloride plastic, that's PVC, which PVC pipe, is one of the most has one of the greatest electron affinities, and so it tends to take electrons. So whenever you rub plastic against your hair, okay, or against your wool sweater or whatever the girl was wearing when she went down the slide, again, you can then see, okay, well, this slide must have become negative and her hair was positive, and that's why it was standing on end. And so you can use this to figure out which materials become negative and which become positive because it ranks them. So this is one of the one that he just did, rubbing a balloon on his hair, and he even said that the balloon takes electrons from your hair, and that's exactly what this animation is showing, and it's what the triboelectric series shows. It shows that your hair tends to become positive, whereas something like a balloon would tend to obtain a negative charge. And when that happens, it does make your hair stand on end, because if all of your strands of hair are now positively charged because they've given up electrons and they're all positive, then they all repel each other. Okay. Obviously, it's more visible if you have fine hair, but it's still happening whether or not it's standing completely on end or not. But you can compare any two objects. They don't have to be really far apart. They could, in fact, silk is kind of smack dab in the middle. If it's higher, it becomes positive. Okay, if it's lower, it becomes negative. Even if they're right next to each other, silk and paper, same thing. Okay, but here I have silk and PVC, which could be what the example was from that animation at the beginning. Some rag made of some material, maybe it's silk, maybe it's nylon, whatever. But this rag becomes positively charged and the PVC pipe becomes negative. All right, so friction is one way that charges can transfer. Another way that you can transfer charge is by conduction, touching a charged object. Some of you guys did this when you touched the surface of the metal dome on the Van de Graaff, like this kid is doing here. Again, conduction means you're touching a charged object and a neutral one, or you could just have two objects that have different charges. It doesn't have to be charged and neutral. But what happens when you do that is that charges flow between the objects until they reach an equilibrium. Because if like charges repel, you're not going to get a bunch of electrons all concentrated in one area. They're going to spread out until everything is balanced. And so if you touch a charged object to a neutral one, or two objects that have different charges, the charges will distribute themselves as far apart as possible so that everything ends up balanced out or at equilibrium and with the same charge. Charging by conduction does typically happen with conductors because the charges can flow. And so it's typically going to be between metal objects. But obviously if you touch a Van de Graaff, there's enough voltage there to force some of those charges into you too. So you can have it with that. In fact, that's what we did in class. And so, for example, the Van de Graaff generator, if it's generating a bunch of these negative charges and you touch it, then the strands of your hair end up negatively charged. And they stand on end because they're all of the same charge and like charges repel. Okay, but again, typically you'll see different examples involving conductors. So let's talk real quick about what a conductor is versus what an insulator is. A conductor is a material that allows the flow of electrons from atom to atom. So we're thinking of metals, typically, when we think of conductors, although you can have some of your semi-metals that have conductive properties as well. An insulator, on the other hand, does not readily allow the movement of electrons. And again, this animation is showing that. You also saw this in the animation on the Java Lab site, or again, perhaps in the video if you couldn't get the site to load. But that's the difference between the two, is how readily they allow the electrons to flow. So if you have a conductor and you touch a metal or a negatively charged object to it, then your electrons will disperse themselves because they're able to flow freely. Whereas if you do the same thing with an insulator, your charge will stay in that one area. Like if you rub a balloon on your hair, the charges stay in the part of the balloon that you rubbed on your head. Okay, and so they don't flow easily or really at all because a balloon is made of rubber, and rubber is a very good insulator. All right, so here's another thing you could do is some basic math. Okay, we're not going to do any complicated calculations with this, but I could ask you, hey, if I touch a negatively charged rod to a neutral sphere, what is the charge afterward? And here's an example showing just that. This rod shows a charge of -4, okay, and the sphere is neutral, so the charge is 0. Again, Q is charged. And over here, after they have come into contact, because these electrons want to distribute themselves evenly, if this one has -4 and this one doesn't have any, then you're going to end up with -2 and -2. They're going to spread out until you reach equilibrium. Okay, and so again, you'll end up with two objects. When you have charging by conduction, you will end up with the objects that touched each other having the exact same charge at the end. Okay, so they'll end up with the same charge, so that gets split in half and shared between them, -2, -2. But it doesn't have to be a neutral object. You can touch two charged objects together and do the same thing. Okay, so here I have the same rod with a charge of -4, but now my metal sphere has a charge of +6. So it's missing some electrons, whereas this one has some extra ones. So clearly we're going to see electrons transfer into that sphere. If you want to know how many, though, again, you're looking until you reach a balance. You can do some very basic math to figure this out. Figure out the total charge of your system. So if the rod is -4 and the sphere is +6, then the total charge of the two together is +2. All you do is add -4 + 6. Okay, and then you split it in half because, again, they reach an equilibrium. It shares the charges equally. So if you have a total charge of +2, divide that by 2. Each object would have a +1 charge after these two objects touch each other. Okay, that is charging by conduction, and it's how you can calculate it. Okay, how does it occur? Again, we're looking for electrostatic equilibrium. And so here is what this would look like with a +1. Here is what this would look like with a +1. But it gives you an arrangement of those electrons where they're spread out as much as possible. And so you end up with the same amount in both of, or the same total charge rather, in both of your objects. Please note that the total number of electrons and protons doesn't change. It's just that the electrons can move between the objects. Okay, so you're not creating or destroying new electrons, you're simply transferring them. Here's one of the demonstrations we did with the Van de Graaff. You can see the pi 10s flying off. Again, the Van de Graaff generator uses friction between a rotating belt and special brushes to transfer electrons to the metal sphere, giving it a negative charge. And then all those negative charges, because it's metal on metal, can flow into those pi 10s, and now they're all negatively charged too. And they repel each other and fly off. We saw this in class before spring break. So it says, given this, why do the aluminum pipe hands behave as they do? And again, it's what we just said, like charges repel. It's a conductor, it's a metal. The electrons flow into those two, and they repel one another, and they fly off one at a time until you don't have any more sitting on top. Again, this is what's happening if you want a visual. When it's off, it doesn't have a charge and everything's neutral here. When you turn it on, there's a whole bunch of extra electrons that then flow in here. The protons are still there, I just didn't illustrate them. And like charges repel. All right, grounding. Grounding is a term that you definitely need to know, and it's something that I mentioned when we used the Van de Graaff as well. In fact, I said, hey, in order for this to work, you need to stand on this stool because as soon as you touch the ground, the electrons will flow into the ground, and that's what it is. Grounding is the process of removing excess charge on an object through transfer of electrons with the ground, with the earth. Okay, so when a charged object is grounded, excess charge is balanced by the transfer of electrons between that object and the ground. It's basically a neutralizing or uncharging process. And again, those of you that touched the Van de Graaff, as soon as you stepped off of the stool onto the ground, your hair came back down. Because of that, it was able to transfer with the earth, which basically think of as a limitless supply of electrons if they need to transfer into you, or it can absorb a limitless supply. It's not technically limitless, but that's how it behaves. Okay, and so you can have this exchange between you and the ground, or some charged object and the ground. Grounding uncharges things. In order to build up a static charge in a chain of students during our Van de Graaff demo before spring break, everyone had to be insulated from the ground. When we tried it out, I made everybody sit on a desk for this very reason, because whoever stood on the ground and then touched your finger, again, some of you guys did that, you touched the person who was touching the Van de Graaff, you felt it. You felt the transfer of electrons flow from the ground through you to them, or if you were the one on the stool, from that person to you, but it's because they were connected to the ground and there was a pathway and a shock that you felt whenever that happened. All right, guys, for the rest of the class period today, you now have time to work on your assignment, 1102.2 charging problem set. You'll find it in my open math. It is due by 11:59 p.m. tonight. So please go ahead and work on that. The other thing that you could choose to do with your time right now is have a discussion with your group that you picked yesterday for your electric house project, and maybe open up that planning sheet. You only need one planning sheet per group, so you could get that opened up and just start typing IDs in there if nothing else. Obviously, you need to share the sheet with your group if you're using your sheet. If you're typing into somebody else's sheet, they need to share their sheet with you. Just as a reminder, you guys have a quiz this week on Friday. That is when our unit, tomorrow's our last day of notes. So our quiz is on Friday, and it's going to be a CFU in My Open Math. And then your test is going to be on Monday, on paper like normal. But your quiz will be digital on Friday. All right, guys, go ahead and get to work. If you have questions for me, let me know. And if you don't finish 1102.2 during class, then you do have homework tonight.